Welcome back, guys. In today's lecture, we continue talking about variables, and we'll talk about local variables. In particular, stack allocation, store and load architecture, and also we'll introduce type annotations for variables, which later we will reuse for function parameters. So let's actually start from the type declarations today, and then we'll switch to local variables allocation. Okay, so here's our example from the previous lecture. We have the global variable version and the local variable version of a different type, right, of type string. Now there are two problems here. First of all, the local variable currently overrides the global variable, and it also has different type, so it's actually an error. And let's use simple variable names, since we have version already installed in the global environment. In the compiler, let's just use variable x. And let's start annotating our variables with types. So as we said, by default, we'll be using just i32 type for all the values, that is the number type, or we can actually annotate a variable name or a parameter with a type, and in this case it's becoming a pair. The first element is the name and the second is the type. Okay, so we take the name declaration, which can be either the simple name or the list with the name and type, and we have to extract the name and the type. Let's exactly introduce this helper method, extract var name. And instead of just creating global variables, we need to handle this generically for local variables and global variables. Now, first of all, we need to have the type, right? Again, we're going to extract the type, which by default will be just i32. Then we actually need to allocate the variable, right? We'll introduce the helper function, alloc var, which accepts variable name, its type, and the environment where it should be added. And once we have the allocated variable, we have to store its initializer to the binding of this variable, right, which will be allocated somewhere on the stack, and we will store the initializer value into that location. In this case, in contrast with just global variables, this might be any expression. That's why we have the store instruction. And we have the note that local variables are allocated on the stack. Now, to remind you, stack memory is automatic. Every time we enter the function, a stack frame is allocated, which is used exactly for local variable storage. And later, when we'll introduce classes, we also introduce heap allocation. For now, we'll be working just with the stack. Sounds good. Let's start from our helper functions. Extract variable name, right? Two cases. If it's a list, then we take the second element. Otherwise, just the variable name. Plain simple. The same we do with the extract variable type. If it is a list, we introduce the new function, get type from string. Otherwise, as we said, default is i32, just to make our test more convenient. Okay, let's go down, get type from string. Now we'll be using generic number type in our code, which roughly will be equivalent of i32. That's exactly what we write. If the type is number, we treat it as i32. What else we have? We have strings. And from previous lecture, we know that string is the character pointer, i8 star. And by default, for now, let's just use i32 as well. Right, this is where no type is specified. Okay, so that should be it. Now let's get back to the variable access. So here we handle only global variables for now, but we should start handling the local variables as well. Now the local variables, in contrast with the global variable type, are handled by the alloc a instruction. Alloc a is exactly allocation variable on the stack. So from our environment, if we're able to cast the value to the local variable, we should just load this variable from the stack. For this, again, we get the type of the allocated variable on the stack. Right, we pass the actual local variable, that is location on the stack, and the variable name. Okay, let's try it. And we forgot the main part, of course, the variable allocation itself. Right, so let's implement it. And as we said, we need to accept the variable name, its type, and the environment where this variable will be added. Now, and here we should say that all the local variables should be allocated at the beginning of the stack frame. Right, something can be pushed onto the stack during the execution, but all the variables are usually at the very beginning of the stack frame. And since our builder just continues emitting the code, it might already be somewhere deeper in the bytecode, so to emit at the beginning of the function, let's introduce a second builder. Right, nothing prevents us creating a second builder instance, which just always points to the beginning of the function, where exactly we'll be emitting the variables. Right, exactly the same as we have the builder. Here we have the vars builder, which will reuse the same module, the same everything, just always points to the beginning of a function where we will be creating the local variables. With this, even if we emit variable declaration somewhere after some expressions, the storage for this variable will always be at the beginning of the function. Okay, let's initialize this builder too. And inside our alloc variable, we explicitly say to our vars builder to set insert point at the entry block of our function, of the currently compiling function. Right, regardless where the main builder is, the vars builder will be meeting exactly here. Now, to allocate a local variable, we use the instruction called alloc_a, as we said. That is the stack allocation. We pass the type, how many slots to reserve, in this case. With 0, we say this is not an array, and we pass the name of the variable. One important note, since we use our environment structure to handle local scope, we have to define this variable in the environment. Right? For this, we pass the name and just the var allocation instruction, which exactly is used when we access the variable, right? We cast to alloc_a instruction. And that should be pretty much it. So let's try it. Let's execute. And take a look, we exactly see the alloc_a instruction, specifically for the variable x. And at this point, we switch fully to the local variables to the main function. To create actual global variables with the ampersand, feel free to handle them separately. For now, we'll be treating them as locals to the main function. So in this case, we create the local variable x. Right, you see the alloc_a of i32, our default type. And then we see the store instruction, which actually sets the value of this variable, which at this point might be either constant or any expression. And we see we set value 42 to the variable x. That is, we pass the address of this variable on the stack. Now, going down, we see the second variable x is allocated. But in this case, it's named x1 by some reason. And at this point, we should talk about a concept which is called static single assignment, which is used by multiple compilers for different types of optimizations. And what this means, you may have only one variable with the same name. Right? For the second variable name x inside the block, we cannot use the name x again. So the compiler, LLVM compiler, automatically renames it to x1. Now, our environment structure will be able to handle this automatically, even when we search by the x name. Right when we access the variable name inside the block, you can see correctly the x1 is used, but not the original x. And in this case, we store exactly the string to the inner variable x1, but not the number. Now, also important point, to use the value, right, when we want to print the inner variable x, we have to load it again. And that's exactly the consequence of the load store architecture and the static single assignment. So once again, the static single assignment allows for multiple optimizations for the compiler. That's why each time it uses the variable, it always creates a new variable. Now, of course, all these things will be optimized by the optimizing compiler, but renaming and creating each time a new variable is exactly needed to be able to apply those optimizations. So when we want to print the variable, we load variable x1 into new variable x2. And in fact, exactly at this line, we already have the problem. The thing is, since we don't yet introduce a new scope, a new environment for the inner block, it tries to overwrite the original variable and says the types mismatch. So let's actually go ahead and fix it inside the block. Before going to evaluation of each instruction, we have to create a new environment, right? Passing our environment as the parent. And our block should be evaluated, of course, in the block environment, not in the outer environment. With this, we'll be able to find the inner variable x right away with the correct type. Right, so in store instruction should just work. Let's try again. And no, we still have the issue. Let's see. Oh, that's because we allocated inner variable type with the i32 by default, right? So we have to annotate it with a string explicitly like this. So let's try again. And that's exactly correct. Now, as an assignment, go ahead and infer type automatically from the type of the initializer, right? For example, we see here hello is definitely a string, so we may omit the string type annotation. But for now, we have to specify it explicitly. And as you can see correctly, printf printed the right variable x. Inside the block, it's a string. And once we exit the block, it's again the number. And this is because our environment resolution scope chain just works, right? It traverses the full environment. And LLVM automatically renames all the variables as it needs to keep the static single assignment form. And finally, let's implement the variable assignment, right? That is the updating the value of a variable. For this, we're going to use the set instruction, right, which sets the variable x. So in this case, we should see value 42 and then the value 100 after it's updated. Let's quickly introduce this instruction, set. And the handling is simple, right? We just take the name. In this case, we don't need to annotate this with the type because the type should match to the one which is used when the variable was declared, right? With the variable declaration. So just take the string name. Then we'll look up the actual variable in the environment. And this will return either the global variable or the alloc_a instruction. And once we have this binding, we should be able to call the store instruction again, right? Similar as we use when we declare the variable. So create store, pass in the new value, and we of course need to gen this value first, evaluating in our environment. Okay, so that should be it. Let's go ahead and test, and it works. As you can see, again, value x is 42, and after the update is 100. Notice correctly we use the original variable x from the outer scope. That is our environment resolution return correct binding. Okay, so that's it for today. We now have variables, local and global, and in the next lecture we'll start talking about control flow, branch instructions, etc. That's it for today. Thanks and see you in the class.